get to the end of year 2.
All right, so we're 6E, shortest distance between a point and a line. And we're starting in 2 dimensions. And our first example, we'll get straight into it, distance between a point and a line. Now this here is what we call, it's an axiom of mathematics. It's not something that you can demonstrate deductively, but it's something that we assume because it's sort of intuitive for us. And that is that if we have a line and a point, okay, the shortest distance from the point to the line is going to be a perpendicular path, okay? And so you can look like these ones are sort of a bit longer than that one. So it's something that's intuitive, something that we can't prove deductively. It's an axiom that we hold in mathematics. Okay, so we've got, so if it's when they're perpendicular, it's when the dot product of them. So in the example that we've got here of the formula, we've got R is some point that lies on the line. Point P is going to be closest to the line when PR is the dot product of PR and the direction of our vector is 0, because that's when they're perpendicular. So we've got, find the shortest distance from the point 4 minus 1 to the line x equals 3 plus t, and we've got y equals minus t. Now we're going to change this point a little bit because I was doing this example before, and this point actually lies on the line. Okay, so it's sort of what, you know, the point lies on the line, so the shortest distance that doesn't really exist. So let's just come up with a random point. Let's choose x is 5 and y is 10. Okay, we have the line, the point x is 5, y is 10. And so we could think about sketching that on the Cartesian plane, you know, 5, 10 is about there. And then for the line that we've got here, it passes through the point x is 0, x is 3, y is 0. The x value is 3, the y value is 0. Like you can think about this as it's 3, 0 plus t times, and we have 1 for x and minus 1 for y. All right, so when you think about, here's the parametric equation, here's the vector equation. So x is 3, y is 0, so that would be like there, and it's going across 1, down 1. All right, across 1, down 1, across 1, down 1. So it's this line here. All right, and so the shortest distance then is going to be somewhere up here, isn't it? It's going to be when they're 90 degrees to one another. So what we're going to do is we're going to come up with this point R that lies on the line. Now R, the coordinate of R, all right, is going to be 3 plus t and minus t for some value of t. Like t exists everywhere along this line, okay? So what we're going to do then is we're going to say, well, what is vector PR? What is the vector from P to R equal to? Now the coordinates of R, I've said, x is 3 plus t and the y value is minus t. We've got the coordinates of P. So the vector from P to R is just the coordinates of R, take away the coordinates of P. All right, so vector PR then is going to be 3 plus t, take away 5. It's going to be minus 2 plus t for the x component. And for the y component, we'll have minus t, take away 10. Okay, so that's vector PR. And then they're going to be perpendicular when PR, the dot product of PR and the direction of our vector, so I'll make this as an argument, perpendicular when PR dot the direction vector equals 0. So we have 2 plus minus 2 plus t, minus t take 10, dot 1 minus 1 equals 0, and we'll solve through for t. So what are we going to have? Minus 2 plus t, and then we'll have plus t plus 10. So we'll have 2t plus 8. 2t is 8, t is minus 8, t is minus 4. Okay, so if t is minus 4, now we can find the coordinates of R. All right, so we can say, well, when t is minus 4, the value of r is going to be 3 plus minus 4, so that's x is minus 1, and the y value is positive 4. Minus minus 4, positive 4. So that's the coordinates of r. We've also already got vector PR, the vector from P to R. And so, like vector PR, if we evaluate that, we'll have, minus 2, take 4, and we'll have minus 4, take 10, minus 16. And so then the modulus, what we're interested in is what's the shortest distance? Well, that means what's the distance of PR? What is the modulus of vector PR? So that's essentially what we're breaking it down to find here. So I'll write out here, the modulus of PR, the shortest distance when they're perpendicular will be 16 squared and 6 squared. So 256 and 36, and then the square root of that will evaluate to 3 significant figures. 6 squared, 16 squared. We've got 2 root 73, 17.08. 17.1 grid units. Okay. Now, this is why I messed up. Minus 4 becomes positive 4. Positive 4 take 10. That's 6. It will be minus 6. So, that's going to affect it. Square root of 72. And it's a bit smaller. That sounds a bit better. 485, 8.49 grid units. Okay, so that's our first example. All okay with that? Clear it off. We'll sketch up our second one. So we have in the next one, a house is located at x is 1, y is 1, and a road runs along the line 2x plus y equals 3. Determine the shortest distance between the house and the road for a driveway. We love a good application of mathematics. So let's just sketch it first. So we have the house is located at x is 1, y is 1, so that's going to be here. We'll call that h for house. And the line is 2x plus y equals 3. So this is the line in general form, and this is probably a good opportunity for us to recap how to graph in general form, because graphing in general form is actually a fair bit easier than y-intercept form. Okay, because what we can see is the y-intercept occurs when x is 0. So if x is 0, the y-intercept is 3. So I've got 1, 2, 3, that's my y-intercept. Okay, and my x-intercept occurs when y is 0. So I have 2x is 3, and we have x is 1.5. So that's going to be like here. Move that down a little bit. They're very close. So here's the road, and here's the house. Okay, so that's going to be when the shortest distance occurs, is when they're perpendicular. So what we need to do then is we need to come up with this line in vector form. Okay, how can we describe this line in vector form? So if you think of this line, right, you can think of it in y-intercept form, you can think of it in general form. It has a slope of minus 2, right? It's going across 1, down 2, across 1, down 2. So if it's going across 1 and down 2, this is the slope, right? I didn't even think about it like that. Minus 2 on top of 1. Across 1, down 2. So as a vector, across 1, down 2. That's the direction vector of the road. Okay, so that's our road, and then it passes through. We can use any coordinate. We know this is x is 0, y is 3. We know this one is x is 1.5, y is 0. So we can use either of those coordinates as the starting point. It doesn't matter. But this line, if we describe it in vector form, the line of the road is going to be some coordinate, let's say 0, 3, plus some parameter multiplied by the direction. Okay, so we've got the equation of the line there in vector form. So now, let's find, well, what's the coordinates of R? Okay, this point where the driveway from the house hits the road, all right? So we know the house is x is 1, y is 1. So the coordinates of R are going to be x is 0 plus t. So we'll just have t for x, and y is 3 take away 2t. For some value of t, R lies on the line. We're trying to identify what's the value of t that makes it true. So this means vector HR from the house to the road. All right, coordinates of R take the coordinates of H. So we'll have t take 1 for the x component, and we'll have, we've got 3 take 2t, take 1, 2 take 2t. Okay, so we've got the vector from the house to the road, and now they're going to be perpendicular when the vector from the house to the road dot the direction vector of the line equals 0. That's when they're going to be perpendicular. So we'll evaluate this. We've got t take 1, and we'll have minus 4 plus 4t. So here we've got 5t, and we'll have take 5 is 0, we'll have t is 1. Okay, so we can identify the coordinates of where the driveway meets the house. When t is 1, the coordinates of R are going to be 1 and 1. Maybe this is the one I was talking about where it lies on the line. 1, 1. When x is 1, y is 1. 2 plus 1 is 3. This is the one that lies on the line. So the shortest distance is the house is on the road. Okay? So how can we identify that based off the working out that we've observed here? Okay, when we put t as 1 into the coordinates, we see that R and H have the same coordinate, and so thus H lies on the line. And we probably could have identified it a fair bit earlier on if we'd substituted the coordinates of the house into the equation of the road, and we'd see that they lie on the same point. Okay, so next time I'll change that example a little bit as well. So the shortest distance is 0 grid units because it lies on the road. Okay, so let's give 6E a bit of a crack then and float around, see how we're all feeling about what we went through yesterday, 6C and 6D. So just dot product between some vectors, making it equal to 0, solving for our parameters.